Bioinformatics Micromodules, Principles of Dynamic Programming. In this module, we'll discuss the basic principles of dynamic programming, which is a powerful way for solving sequence alignment problems. The reason that we need dynamic programming is the large number of valid alignments for a pair of sequences. Here is a table showing the number of valid alignments for a pair of sequences of lengths m and n respectively. You can see that even when m and n are just 10, the number of valid alignments is already 8 million. And this number actually grows very rapidly as m and n increase. So it's practically infeasible to enumerate all the possible alignments in order to find out the optimal alignment with the highest alignment score. So how do we find out the optimal alignment? The basic idea behind dynamic programming is to derive some smaller subproblems of the original problem. We solve these subproblems, and then we combine their results to solve the original problem. Notice that in step 2, if the solution to a subproblem is obvious, of course we can obtain it right away. On the other hand, if it is not obvious, we can still recursively divide it into smaller problems, and then we repeat the whole process. To illustrate how to use this idea to solve sequence alignment problems, we use a simple example. Let's say we want to align these two sequences R and S of lengths 2 and 1 respectively. We're going to use a very simple scoring scheme with a +1 score for a match and a -1 score for a mismatch or indel. We also need to introduce a notation, which is the square bracket. When we write R square bracket 1 ... 2, it means that we extract the subsequence of R from character 1 to character 2. Similarly, we can write R2 ... 2, which means we extract only the second character. So in order to solve the sequence alignment problem, we first consider how do we deal with the first characters of these two sequences. There are three possibilities. The first possibility is we align R1 with S1. And then we have a new subproblem, which is to align the second character of R with an empty string. Of course, it is obvious to us, but then in order to systematically analyze every case, we will still try to divide the problem in this way. The second possibility is we align a gap with S1, and then we have a new subproblem, which is to align R1 ... 2 with an empty string. Finally, we can align R1 with a gap, and then we have a new subproblem, which is to align R2 ... 2 with S1 ... 1. We can also visualize this whole process by something called a recursive tree. The original problem is to align the whole R with whole S. As discussed, there are three possibilities. The first one is to align R1 with S1. We know that since these two characters are not the same, we have a score of -1. And we have a new subproblem, which is to align R2 ... 2 with a gap. So this is obvious. We know there's only one way to do that. And there will be a -1 score for that. In the second possibility, we align a gap with S1. Again, since it is an indel, we know there will be a -1 score. And the new subproblem is to align R1 ... 2 with an empty string. Again, it is obvious that there's only one possible way to do this alignment, which is to have two gaps in the second sequence. So there will be two indels and the score will be -2. In the third possibility, we align R1 with a gap. Again, it is an indel, so there will be a score of -1. And then we come up with a new subproblem, which is to align R2 ... 2 with S1 ... 1. For a computer, this is actually not obvious, because there are still three possibilities. You can align R2 with S1. Since they are the same, both of them are G, then there will be a score of +1. And there are no new subproblems, so the score of the subproblem is 0. Or we can align a gap with S1, which will introduce an indel with a -1 score, and we have a subproblem, which is to align R2 ... 2 with gaps. which will further introduce a -1 score. And finally, we could align R2 with a gap. This alignment itself will have a -1 score, and we have a new subproblem, which is to align empty string with S2.2. Again, there's only one possible way, and the score is -1. Now, consider this lower branch. For the three possibilities, if we take the first one, the whole score is 0 plus 1, which is 1. For the second one, the whole overall score is -1 minus 1, which is -2. For the third one, it is also -2. Therefore, by comparing the three possibilities, the best one is the first possibility. So we take that, and now we have a partial alignment, which is to align R2 with S1, with a score of 1. Now we go back to the first step. Among the three possibilities, the first branch will lead to a score of -2, the second one -3, and the third one will be -1 plus 1, that is 0. So the third branch is the best one. So we take it, and we get the optimal alignment of A aligned to a gap, G aligned to the G, and the overall score is 0. So in general, we can always divide a problem into simpler subproblems in this way. Using our notation, if the two original sequences have lengths m and n, then the original problem is R1.m trying to align with S1.n. We don't know what is the best way, so we try out three possibilities to align the first one. So we can align R1 with S1, resulting in the first subproblem, which is R2.m with S2.n. Or we can align a gap with S1, which leads to the second branch. Or we can align R1 with a gap, which leads to the third branch. And then for each of these subproblems, we can do the same thing to invent more and more subproblems. So now you may be wondering, is it really a good idea to do dynamic programming in this way? Because it seems that there will be a large number of subproblems to solve. The first layer will have one problem, second layer will have 3, third layer will have 9, and then 27, 81, it grows very rapidly. But if you are careful, then you can see that actually different branches share common problems. It is a very important characteristic of dynamic programming, which means that if you have solved a problem once, later if you need the solution to that problem, you can simply reuse it. To see that, I have used some colors to highlight the same subproblems. For example, you can see that I have used red to color the subproblem of aligning R2.m and S2.n, and there are already 3 occurrences of them. So instead of solving them again and again, we just reuse the problems. We save the solutions. Next time we need to solve these problems, we take the solution directly from our storage. So now the question is, if we analyze in this way, is it really better than enumerating all possible alignments? In order to answer this question, we need to notice that each subproblem is actually trying to align a suffix of R and a suffix of S. Here, suffix means that we cut out some of the characters from the beginning of the sequence and align the remaining part. So, how many suffixes are there? For R, since the length is m, the whole string is one suffix, cutting the first character is one suffix, and so on. Finally, if we cut out all characters with just the empty string, it is also a suffix. So altogether, there are m plus 1 suffixes for R. Similarly, there are n plus 1 suffixes for S. Therefore, the total number of alignment problems that we need to solve will be m plus 1 times n plus 1 minus 1, which is about mn when m and n are large. The reason that we have minus 1 is because we do not need to align a gap with a gap. So here, when m and n are large, m times n is just a polynomial function of m and n, which is much better than an exponential function. To give you an idea how much saving we have achieved, let's consider m equals 10 and n equals 10. Previously, we have seen that if we enumerate all possible alignments, there are 8 million alignments that we need to compare. However, if you use this subproblem solving scheme, there are only 120 unique subproblems that we need to solve. This is a big improvement and making dynamic programming a very powerful way to solve sequence alignment problems.